there, everybody. We'll go ahead and let folks start coming into the Zoom room here. As people come into the Zoom room, I wanted to see if we could get folks chatting to each other. So as you get settled in, get comfortable in front of your computer, go ahead and navigate to the bottom of your Zoom window and go ahead and let us know if you caught the Aurora Borealis this week, or I guess this weekend. I know a lot of us from all over the country got a little preview. And I did want to say, as you are commenting, go ahead and make sure that your chat is set so that everyone can see it. Not only is this a great way for us to get to know each other before the webinar, but it also makes it helpful so that as we're answering your questions during the webinar, other people can see what questions you have asked. So go ahead and navigate down to the chat box and let me know if you caught the fabulous celestial event that we had this week. I, for one, missed it due to being so sleepy, but I have seen a lot of pictures and I'm filled with FOMO, so. All right, it looks like some folks got pictures. Awesome. Yep. Okay, so we're all in it together. None of us saw it. That means that we're the cool people, but we're too cool for school. Awesome. Wow, someone saw it in Germany. Holy cannoli. Awesome. Well, to make the most of our time today, I know we probably have a fewer people coming into the Zoom room, but I do want to hop into some housekeeping items just to make sure we keep today moving and grooving. So the most important thing for you to know is that you will receive a recording of this webinar after we're done talking today. It just needs to be edited a little bit, but as soon as that process is done, it'll be both on our website and on our YouTube channel. That usually takes about 3 to 5 business days. We're going to email a link of that recording as well as our resources folder to you as soon as we're done talking, or once we get that webinar recording up. So keep an eye on your inbox for that. I'm going to drop a link to the folder for today as soon as I'm done talking here. And as I mentioned before, we do want to answer your questions. So if you have any questions, please put them in the chat. Make sure you're set to everyone so that everyone can see your question. But we'll keep an eye on that chat and make sure you get an answer. If we happen to not get to it, please feel free to reach out to us at biology@vernier.com. With all that being said, I'll pass it off to the amazing presenters. Thank you again for joining us.
Well, good afternoon and evening to everybody. Thank you for coming in and joining us as we talk about water quality and using sensors. So just kind of a general today's agenda is we're going to give a little background on water quality just to get everybody kind of on the same mental page there. And going to also do an introduction of me and my colleague Melissa here. And we're going to talk about all the different sensors that Vernier has and the types of sensors that you can use to measure the different parameters that we usually look at in water quality. And with that, we're also going to cover some best practices and kind of some tips and tricks that we have for those various sensors. So just a little background. Hi, I'm Colleen McDaniel. I've been at Vernier now for 10.5 years. Before Vernier, I used to teach in Houston, Texas, where I taught pre-AP biology, grade level biology, and AP environmental science. So water quality was something I covered a lot, especially with my AP students. And then Melissa.
Hi, everyone. I'm Melissa. I'm the Director of Chemistry here at Vernier. I've been here almost 14 years. And before I started here, I taught chemistry at the college level. And yeah, so I also do some water quality technical support and training and product development. So a lot of these sensors are also very near and dear to my heart. So I will be the person furiously answering your questions in chat. So please put those in there. And I'm also going to be interrupting Colleen when we have good questions for her. So please put any and all questions into that chat window and I'll make sure they get answered.
Yes. And don't hesitate to ask a question at any time. That's why we have chat. It makes it very easy to do that. So let's talk a little bit about water quality. Exactly what is water quality? So essentially what we're looking at is monitoring the conditions of an aquatic system. And this can be anywhere from a pond, a stream, a lake, a river, the ocean, a bay, an estuary, pretty much any type of body of water there is, you can easily monitor it to look at different conditions. And water quality is kind of this overarching thing that we're looking at both physical, chemical, and biological factors that are affecting this body of water. So we're looking at the temperature, for example, for physical, chemical, we're looking at nutrients. Biological, we could be looking at macroinvertebrates, what is actually growing and living within this body of water. And it's interesting to think about the levels of acceptable processes within water quality is going to be dependent on the use and dependent on the country. Every country is going to have their own standards for what is acceptable levels in different bodies of water, and it also is going to be dependent on use. The majority of the time when we talk education, especially at kind of the high school, middle school level, we're usually doing a lot more emphasis on the ecological monitoring. How does water quality affect the ecosystem? And that's going to be what we're going to concentrate more on today. There are different standards, though, for things like human consumption. So drinking water has very strict standards that have to be met for that quality. And then also water use for industrial or domestic use. So this would be things such as gray water or water that's used for cooling of different power plants and things like that. And why this is so important for the ecological monitoring aspect is because looking at these different abiotic factors and how they play into that system really helps us get an idea of the health of the system, primarily because all aquatic organisms have really specific parameters that they need to survive. There's going to be some that are going to be a lot more broad and kind of opportunistic, like carp. But then there's going to be some species like trout that have to have a very specific temperature range, a very specific dissolved oxygen range. And if it goes anywhere outside of that range, you're going to see a big die-off and some effects along in that ecosystem there. So one of the first things that I always talk about that we need to make sure we consider when we're doing water quality testing is doing safety considerations. You always want to cover water safety with your students. Ideally, if you're going to be working around larger, deeper bodies of water, making sure that you have the appropriate protective equipment, such as life jackets, and make sure you're aware of how deep that water is. I always give kind of an example of something that I did a couple years ago was I was out getting some water samples and doing water quality testing at a stream that when I looked at the stream, it was only 3 inches deep. But when I went to step into the stream, because I thought it was only 3 inches deep, I then sunk down to my knee in mud because of how much water was saturated through there, and it was just straight mud. So making sure you're kind of aware of those conditions is very important. So with the safety equipment, life jackets, waders are always great. Muck boots. When I fell in that stream, I nearly lost my muck boot because it came up and over it. So I had to dig that out of the bottom of the stream. And one big thing too, it's always good to have a buddy system. So making sure students are working in pairs at least, so that way you don't have a problem of a student disappearing or something and not knowing what happened to them. I always recommend too that sometimes if going into the water is not feasible, that getting a bucket or some sort of collection device can be very useful. For example, when I was teaching, I was in Houston, Texas. So I would do a lot of water quality testing at bayous. And you would not pay me enough money to wander into that bayou because of alligators and alligator gars. So I would literally have a cat litter bucket that I had attached to a string that I would throw down into the bayou and collect my water sample. And that's another safety consideration, is thinking about the types of animals that are around that can cause harm to students in that body of water. So moccasins, alligators, any type of fish. Students might just be afraid of fish. So keeping those things in mind. So what are the variety of sensors that can be used in water quality? So we basically have a lot of different parameters that are going to be looked at in water quality measurements. And the ones I'm going to primarily talk about here are going to be those ones that have a sensor component. So things like a temperature probe, pH sensor, a conductivity sensor, salinity sensor, dissolved oxygen probe, turbidity sensor, and ways to measure nutrients, which there's two ways that you can actually do nutrient measurement. One is doing like a colorimetric standard using chemical kits and from Hoch or Lamont. And another way is doing a direct measurement with sensors specifically designed to test very specific nutrient compounds within the water. So for those of you that are familiar with Vernier might know we have essentially now two different types of sensors. We have Go Direct sensors and LabQuest sensors. Now, the biggest difference going to be between them is LabQuest sensors have to connect to a LabQuest device in order to work. So they have to connect to like a LabQuest 2, a LabQuest 3, or if you're using a computer or a Chromebook, a LabQuest Mini. Go Direct sensors are going to connect directly to your device, either by Bluetooth or by USB. So they can connect to LabQuest 2s and LabQuest 3s, but they can also connect directly to student devices, such as Chromebooks, phones, iPads, things like that. Both of these types of sensors are going to work, like I said, with LabQuest, but also will also work with graphical analysis too, which is one of our apps that is available as an app on phones, iPads, tablets, Chromebooks, or as a progressive web app as well. Now, I like to try to make sure to talk about both Go Direct and LabQuest because there are some water quality sensors that are currently only available in the LabQuest form. And those three main sensors are going to include turbidity, extra long temperature, and flow rate sensors. So those three sensors, if you want to use those, you do have to have a LabQuest device, be it a LabQuest 3 or a LabQuest Mini that would then connect to a computer or a Chromebook. One of the advantages of having a Go Direct sensor over a LabQuest sensor is that a lot of our Go Direct sensors are now multi-sensors. So for example, our dissolved oxygen probe, not only does it measure dissolved oxygen concentration, but it can also simultaneously measure dissolved oxygen saturation. It can measure water temperature and can give you atmospheric pressure readings as well. While our more LabQuest sensors really can only measure one thing at a time. So with some of the Go Direct, it's kind of nice because if you're doing just water quality and you have a dissolved oxygen sensor, there's no need for you to purchase a temperature sensor because one is already built in to that sensor for water. So let's look at our different types of temperature probes here. So for temperature, we have lots of sensor options for temperature. We've got our Go Direct temperature sensor. We have our stainless steel temperature. We have a surface temperature that is both Go Direct and a version that's LabQuest. And then we have our extra long temperature sensor, which is going to allow you to basically look at thermal stratification in lakes. It's going to be a temperature probe at the end of a very long cable, and that is a LabQuest sensor. When we're doing water quality, it is imperative that temperature is actually measured directly on site because if as soon as you take that water sample out, you're going to have fluctuations and changes in temperature, and you're not going to be able to get a very accurate reading and idea of what the temperature of that body of water is. The other key when we're measuring temperature is to make sure you give enough time for equilibration to be reached. So when you put the sensor in the water, it's not going to instantly read the right temperature right away. It's going to take a little bit of time to kind of drift and get into that temperature mode, especially if you're looking at a body of water that is greatly different than basically the air temperature that the temperature probe is currently in. So for example, here in Oregon, I might be at a temperature of 25 degrees Celsius in the air, but my water temperature could be 10 degrees Celsius. So it's going to take at least a minute, sometimes maybe longer, for it to kind of reach that happy medium point. And the other thing to keep in mind is as that temperature is moving, and this goes with all the sensors to reach equilibrium, students are going to have a little bit of anxiety with that they don't know when to capture the value that they need to go. And it's really important for them to learn that as temperature changes they're going to see this dramatic change of it moving in one direction or the other. And so say the temperature is dropping like from 25 degrees C, then it's 24, 23, and it's going and going and going and going. And then we get around 10.5, and then it goes to 10.6, 10.4, 10.7, 10.5. And because it's now kind of in this perfect little range, you're not going to have that exact temperature stop reading, but it's just going to be fluctuating between those few measurements, which will indicate that you are at kind of an equilibrium state.
Colleen, we have an excellent question. I think it's better to explain
Oh,
out
yes.
loud about the extra long temperature probe. And does it actually measure depths, or how do you get depths from it?
So it doesn't actually measure depths. What we recommend is that you actually measure out on the sensor itself and actually do tape after basically at certain measurements that you want it to be at. So I've heard some people do it every 500 centimeters to every meter, and a variation along that so that students have an idea of how deep that temperature probe is going down. All right. So to go on, temperature is actually a very, very critical part of water quality. I found this graphic on Fondreist that I thought was great, that kind of has this kind of major Venn diagram here showing how temperature influences lots of different factors in water quality. That's why monitoring temperature is actually very important. And one of the biggest ones that it impacts that we'll talk about later is going to be dissolved oxygen. The other thing that's really interesting about temperature and monitoring it is looking at the effects of thermal pollution. So we can have a situation where there might be a power plant that is using water to cool, and that water, as it comes out and gets discharged, could be having a superheating effect in an area. And it is good for scientists to be able to monitor that and see what effects that has on the fish population. Because as this diagram that I found about fish in the Great Lakes, you can see fish temperature can be a very important limiting factor on if they can survive or not. There are some fish like trout that have a very specific temperature range that they can live in, while other fish such as bass have a bit more fluctuation of where they can go. The other thing to note with these water quality sensors that I'm going to make sure to talk about is the waterproofness of them. So the Go Direct version of the sensor is waterproof. The LabQuest version is not waterproof. And I would say it's more water resistant than waterproof. And when I say waterproof, that means if you're submerging the sensor beyond the metal shaft here up into the plastic on the LabQuest sensor, you're going beyond the area that it can function at, because this is where all the electronics are, and those aren't going to be covered. All right, let's talk pH now. So pH sensors, again, we have quite the variety of pH sensors available. We have our regular generic pH sensor with a glass bulb. And then we also have our version that is the Tris compatible flat pH. Either sensor is going to work great for your situation. If what's nice is if you teach chemistry, you probably already have a pH probe. Or if you don't teach chemistry and there's a chemistry class at your school that has probeware, they very well might have a pH probe that you could borrow. So if you look on here, you can see somebody I just saw asked Go Direct versus LabQuest. LabQuest sensors are going to have a cable attached to them, and the Go Direct sensors only have a module attached. There's no cable attached to them. One of the important things with pH is making sure to actually calibrate the sensor before you enter and go into the field, because it's going to be a lot easier to calibrate it when you're on campus than it is going to be if you're going out stream side. The other thing you want to make sure is that you calibrate it in the appropriate range. So basically you want to decide, you want to kind of know if your water is more on the acidic side or more on the alkaline or basic side. And so if it's more acidic, like we're here in Oregon, I would be calibrating my pH sensor between 4 and 7. But as I found out this fall when I was in Kansas City for NSTA, their water is very alkaline. And so for that, I would calibrate my sensor between 7 and 10. Ideally, you don't want to have to calibrate between 4 and 10 because that's going to be such a wide range that you're going to lose some of the accuracy in there because it's so large of a range. The other thing is just
Colleen,
like, yeah.
Sorry, not to interrupt your train of thought, but can you give a little more specifics on the difference between Go Direct and LabQuest sensors? Which one's which in your images here?
Yeah, so the LabQuest sensors are going to be ones that have cables on them that are going to attach by this white connector called a BTA to a LabQuest. And the Go Direct sensors are going to have this module on top that is just an electrode amplifier. Would a wetland? No, so I see a question here. Would a wetland pH calibration be different from a local water pH? Probably not. I find that they tend to be pretty consistent with each other. One great way to find out what the pH of different bodies of water that you're looking for is looking at I believe it's USGS website has some great water quality standards out there of different measurements of places they're monitoring to help kind of give you an idea of what the water quality is for your area. pH is another one like temperature. You're going to want to give it time to equilibrate. And what I sometimes recommend is when you have a pH sensor, you're storing it in a pH 4 potassium chloride solution. And that is how it should be stored. But often pHs of water are going to be a little closer to that neutral range. So if you want to cut down the time of waiting for that equilibration to take place, I typically tend to soak my pH sensor in a pH 7 buffer about 3 hours before I go out and do the readings or the night before. And that just kind of gets the sensor primed in more that neutral territory. So that way it can equilibrate a little bit faster when you go out and do readings. pH is one of those readings you can do it on site or you can do it later on your campus. And I'm going to talk about sample preparation and storing a little bit later here. The biggest key thing is both the Go Direct and the LabQuest sensors are not waterproof. So basically you do not want to submerge them much more than 2/3 of the sensor body right here. Is because the Go Direct sensors have this BNC connector here that is not waterproof. Same thing with the LabQuest pH sensor along with the body here are going to have some electronics in it that are going to cause some issues if they get wet. One of our jokes around here is we say everything is waterproof at least once. And then after that, not so much. So that's something to keep in mind. I have a link in here that Melissa and our other colleague Noose did a great webinar a little while ago about basically everything you could possibly need to know about pH sensors. So I highly recommend checking out this webinar because it talks about maintenance, it talks about storage, it talks about proper use, calibration, all of those great things that really help with how to use these sensors. And I can also show you, we have some great resources on our website specifically for all of our sensors, and I can quick show you here how to access those resources. So if we go to the Vernier website here, I'm on the page for the pH sensor. And if I scroll down, there is a tab over here that it says support. And if I go to support, I can then go to the FAQs and troubleshooting tips. Now, this is kind of what I consider the Vernier cheat sheet, that if there's any problems you have or questions that come about with sensors, this is where I would have gone when I was teaching. And as I go through here, we talk about our troubleshooting steps. And then we have this great video here that shows the process of actually calibrating a pH sensor, specifically using a LabQuest 2, but the calibration process is not all that different on a LabQuest 3 as well. And it's a little different for the GoDirect sensors in graphical analysis, but conveniently, we have videos for those sensors as well on their FAQ pages as well. All right, so back to pH here. So pH, like temperature, can also have a great influence on the type of aquatic organisms that are going to live within a specific body of water. So I found another on Fondreist, again, this great graphic here that kind of shows the different ranges we have with pHs. And so basically, ideally, fish are going to have the best viability between a pH of 6 to around low 9. So that's going to be kind of their ideal pH range. They can live and survive in pHs a little bit lower and a little bit higher, but it is going to cause some stress on them. And when the animals are going to get stressed, it's going to cause a situation where they're more likely to get illness and then potentially die. But you can see is once you get above 10 or below 4, you're going to start seeing some massive fish die-offs in those locations. And that is going to be something you want to monitor and see what might be actually causing that change in the pH of the area. All right, moving on. So for another measurement here in water quality is looking at our total dissolved solids. So total dissolved solids are going to be any dissolved inorganic and organic compounds in the water that essentially you cannot see. I believe it's a substance that cannot be filtered by a 2-micron filter, I believe it is considered part of total dissolved solids. When I was doing water quality before I had sensors and probeware, what the method we would use would be have a known volume of water in a jar, weigh that, then actually let the water dry out or bake it in an oven, and then weigh the jar afterwards to see basically what the big change is versus an empty jar. And that gives you an idea of essentially the weight of how many solids were dissolved in that substance. So with our sensors here, we have both a LabQuest sensor and a Go Direct sensor. And I want to show my screen here so you can kind of see some differences between them. All right. So the conductivity probe that is Go Direct does not have any basically ranges you have to set. It is at a full range, but the LabQuest sensor is going to have a small switch box on the side here that you then have to basically decide which range you want to actually measure your conductivity in. Most people, what I tell them to do is start in the mid-range, 0 to 2000 microsiemens. And then if the water is below 200, then you're going to want to go to the next range down, which is 0 to 200. So those are how the temperature change, the conductivity varies within a LabQuest sensor there. So like I said, LabQuest sensor is going to have 3 different ranges, while the Go Direct sensor auto ranges. There's no switch. Overall, they have the same range. It's just a matter of how it's broken up. The Go Direct sensor, again, is going to be a multi-sensor, so it has a temperature probe integrated into it as well. Again, something to remember here, the Go Direct version of the sensor is waterproof, but the LabQuest version of the sensor is not waterproof. And one important aspect to think with measuring total dissolved solids is the conductivity probe is a very common probe used by chemistry classes in chemistry. And their units that they use most often are going to be in microsiemens. Most students are going to, 1, either laugh at that, or 2, be like, what the heck is this? I've never seen this before. And as an environmental science teacher, I went, what is this unit? I have never seen it before. But what's great is you can change the units on the sensor so that it's reading milligrams per liter or parts per thousand. And so I recommend in the in the sensor, you actually have that written into a protocol to change those units. In the labs that we have written for doing conductivity measurements, that is part of the procedure, is to change the units to milligrams per liter. The thing to keep in mind with total dissolved solids is because those are essentially looking at ionic concentrations, there is going to be some limits. So the max total dissolved solid reading we can get is 10,000 milligrams per liter, or that's equivalent to about 10 parts per thousand. And those were that's where you're going to be above that freshwater level, but not full ocean water level. So I basically recommend, if you're going to be measuring things that are above 10 ppt, you're going to want to get a salinity sensor. Below 10 ppt, conductivity is going to work great, but you also might want to consider doing a dilution. So if you don't have a salinity sensor, you can use the conductivity sensor. You would just want to dilute your sample so that it's within the range of the sensor itself. And a question I get a lot when people call and ask about total dissolved solids is, what does the value mean? How does it relate to water quality? And the way I kind of think of it and describe it is that total dissolved solids, you're looking more at really a characteristic of that aquatic system. So it is an abiotic factor, but it's not necessarily an indicator of the health of the system. It's more kind of a characteristic that tells you what kind of bedrock you might have in the area, or how many minerals or salts are in the water and in the soil around that area. There has been some research that has shown that if there is a very high total dissolved solid, I believe it was over 300 milligrams per liter or over 500 milligrams per liter, it can have an impact on some aquatic systems, especially very sensitive species like trout, which typically, if you're going to have that high of a total dissolved solid, you're probably also seeing some other indications that have poor water quality, such as a high or low pH or potential temperature changes. Total dissolved solids tends to be a little bit more important for doing domestic or industrial use and monitoring that, because that's going to be kind of where we get this idea of hard versus soft waters, of how much minerals are going to be in the water and how that's going to affect pipes or the actual taste of water as we're drinking it. So salinity is essentially just another type of measurement of total dissolved solids. But specifically, we're going to be looking at situations where that measurement's going to be above that 10 ppt value that I was talking about earlier. This is going to be looking at brackish or kind of more saline bodies of water. So this can be like salt lakes, estuaries, tidal zones, tide pools, and the ocean. And to give you an idea of the salinity, ocean water has a salinity of around 35 parts per thousand. And most of our salinity sensors are really kind of calibrated around that high value there. So what we recommend doing is actually, if you're going to be reading something that's more lower than 35 parts per thousand, we do recommend doing a calibration process within the range that you plan to be on reading. Big things to keep in mind is having that the Go Direct version, again, is waterproof, while the LabQuest version is not waterproof. And that is something a lot of people don't realize because it is used a lot with ocean water. And the combination with the LabQuest sensor of the water plus the salt causes a lot of corrosion and can make that sensor not functional. So just something to keep in mind.
Colleen, we have another interesting question. Someone is planning to raise trout. So they are looking at pH and temperature, but what else would you recommend?
Oh, awesome. I bet you're doing Trout Watch. Really cool program there. So one thing I definitely would recommend is actually the dissolved oxygen sensor, because trout require a very high dissolved oxygen content. And something that could be interesting is having a conductivity sensor to measure the total dissolved solids. What's nice is both the dissolved oxygen and the conductivity probe that are Go Direct both already have a temperature probe built into them. So in that case, you would not have to purchase an extra sensor if you did not have it already. Can the Go Direct salinity sensor go to depth like the long temperature probe? Probably not as deep. The waterproofing is only down to 1 meter on some of these sensors here, while the temperature probe can go a lot deeper. The extra long temperature probe is specifically made to go, I believe it's 25 feet. The salinity will probably only be at 1 meter. The other problem we have is the Go Direct sensors. Once they go underwater, that cuts out the Bluetooth signal. So we have kind of this a little conundrum there with being able to do collection once the sensor goes underwater. All right, let's talk about my favorite, dissolved oxygen. Oddly, this has become my favorite sensor, my favorite parameter to read. And I just think it's absolutely fascinating. The chemistry of dissolved oxygen is just weird and mind-blowing to me. So when we're looking at dissolved oxygen, and this can get really confusing for students, is that we're not talking about the oxygen that is part of the water molecule. That oxygen is already bound up with hydrogen and is water. What we're looking at is how much O2 is actually dissolved directly in the water. So we're looking at actual, basically, oxygen gas being dissolved in water. So we have some other older dissolved oxygen sensors. Right now, the only one that we do currently carry is the Go Direct version. And that's primarily because it honestly is the best. We can make it cheaper than the other versions, and it is such versatility. The nice thing, like I said, with this sensor is that it also measures temperature and that it is actually waterproof. Our older dissolved oxygen sensors work great as well. And most of those are not waterproof or are waterproof only up to a certain point, as in the LabQuest Optical Dissolved Oxygen Probe. I did a great webinar about a year ago talking all about dissolved oxygen and how to measure dissolved oxygen and all of the ins and outs and kind of nuances to make sure to get a good reading. So I've linked that on this slide to go to that webinar, and I highly recommend, if dissolved oxygen is something you struggle with, to go and watch that, because it covers a lot of the key components on getting a good DO reading. Again, like pH and temperature, dissolved oxygen, you want to make sure you give enough time for the calibration, the equilibrium to take place. It's going to kind of, again, take some time for that. I get a lot of questions on it's not reading right, it's not reading right. But if you're looking at a water sample that is a lot colder or a lot warmer than the temperature that you're in, it's gonna take 3 to 5 minutes in some cases to actually take the time for that sensor to reach equilibrium and give a proper reading. Dissolved oxygen, again, is going to be like temperature in that it really is best to read on site. I would say it's not 100% necessary, but it's better to do it on site and directly within the body of water. Basically to reduce the potential of introducing excess oxygen when you are collecting a sample. And that's one of the biggest, I would say, variables that you might come across with that. Again, dissolved oxygen, like pH, like temperature, very specific windows for animals and organisms to live in within those amounts of dissolved oxygen. Basically, once you reach below a dissolved oxygen concentration of 6 milligrams per liter, you're going to start seeing stress on your fish, and the fish eventually are going to succumb to basically hypoxia. They're not going to actually be able to breathe. So it's a really important thing to monitor and keep in mind. One of the other components that we often measure with water quality is looking at the biological or biochemical oxygen demand, or BOD. So essentially, BOD is looking at the decomposition of organic compounds within the water sample. And we're doing that by essentially measuring oxygen consumption. So the students will take a sample at site, get a reading, and then take another sample, make sure it's airtight, and usually also wrap it in foil to make sure it's light sealed, and then let it sit for 5 days, and then do another dissolved oxygen reading to get an idea of basically how much microbial decomposition activity is taking place in that water sample, which gives a good correlation of how much organic matter was present. So I see a couple questions asked here. So does the optical sensor require flow over the sensor like the galvanic sensor? It does not. And that is one of the very nice things about it. The Go Direct sensor, the optical version, of also the LabQuest version that's optical, does not require stirring. It does not require warming up. It is automatically calibrated with temperature and pressure, so there is no need to do anything with it. It is literally, you connect it and you can start getting readings right away. So the old sensors do fit perfectly in the standard BOD bottles. The newer version, the Go Direct version of the optical dissolved oxygen probe, that's why one of the reasons that we moved more towards that is because the diameter of that is a lot smaller. It's the same size as our older galvanic one, so it can fit very nicely within those BOD bottles. Okay, turbidity, another one of my favorite love sensors here. So turbidity is basically looking at how clear the water is. How it's very closely related to total suspended solids. which kind of can go into a little bit more of like looking at, leaves and tree bark and things like that that might be suspended in the column. Turbidity, you're looking at more of those kind of microscopic things that could be reflecting light and causing cloudiness in the situation. Currently, we only have a LabQuest version of the turbidity sensor. Something I forgot to put on here right away is that it's one of the sensors that I do recommend calibrating before using. So for water quality, pH, turbidity, and then when we get to nutrients, the ISEs are the three sensors that I say pretty much you need to calibrate before you're going to do water quality measurements. I often recommend teachers to go ahead and get multiple cuvettes. So the sensor itself comes with a 100 NTU standard and one empty cuvette to do sample readings in and zeros. I recommend getting extra sample bottles because that way you can just get one turbidity sensor and students can go collect their own samples and come back and do the readings at kind of like a turbidity station, if you will. The turbidity sensor, like all our other LabQuest ones as we've been going, is not waterproof. So you cannot just take the sensor and dip it in the water and take a reading. Does not work that way. And I get a lot of questions of why a turbidity sensor over a Secchi disc. I used Secchi discs before and they are great in deep water. If you're looking at a stream or a pond that is really shallow, or you're not able to get to the actual center of that body of water, a Secchi disc does not work very well. So that's where I kind of like having that turbidity sensor because it adds that value of being able to do it in no matter what condition the body of water is. Again, turbidity is one of those, ideally, you can measure it right away on site. That is going to be best, primarily because the particulates that are suspended in the water can settle out. But it can be measured when you get back to campus as well. What you just want to make sure to do is to agitate that sample gently before doing a reading to make sure everything is kind of stirred up. Turbidity is a great measurement because you can look at it. It allows you to do comparisons to look at algae growth, runoff, nutrient load, erosion, everything like that. And high levels of turbidity can harm aquatic life. There's situations where fish might have particulates getting caught in their gills to make it difficult to breathe or cause irritation, or the water could get so cloudy that plants can't do photosynthesis. So I'm going to speed up a little bit because I'm getting short on time here. Sorry, I like talking about water quality, so I could just go on for another hour pretty easily. So nutrient testing is a question we get a lot of, we often get a lot of requests about how to do nutrient testing. Now, nutrient testing is very important because in most aquatic ecosystems, you want very low levels of nutrients. The way I think of it is too much is a bad thing, and primarily because it can drive algae blooms, which can essentially end up choking out the rest of the ecosystem by sequestering basically by their decomposition as they die down, it starts to sequester all the oxygen that they released into that pond. The three main nutrients that we talk about are nitrate, ammonia, and phosphorus. So nitrate and ammonia, we have two options to do readings with. You can do a colorimetric assay where you would use a spectrometer or a colorimeter and essentially get a kit from either Hawk or Lamont, and it would be various pillow packets and kind of chemical combinations you would make. But you would basically do, for those chemists out there, a simple Beer's Law type measurement where you would have to create a standard curve and then you would test your sample against that. Sample prep is very intense. There is the issue of chemicals, and in some cases, these can be some very hazardous chemicals that do need to be disposed of properly. A direct measurement method is using our ISEs, or ion selective electrodes. And these are going to be what we call species specific. So we have a very specific electrode that is just for nitrates. We have one specifically for ammonium ions and a few others for other chemistry purposes. Nitrates and ammonium ions are the ones we concentrate most with water quality. They do have calibrations that need to be done again before use. There's no prep you have to do for the sample, but prepping the instrument to do the calibration is what we would consider more intense. It will take up to an hour just to prepare the sensor to get ready for data collection. And this is a sensor that I typically do not recommend doing for middle school or lower high school. This is something that you want kids that have a very good chemical hygiene and chemical processes that they're used to doing. So it's something I recommend for usually advanced high school into college. Phosphorus, there's only a colorimetric assay available. There is not a ion specific electrode for those. And the way I kind of look at these is when you're doing these nutrient testing, colorimetric, it's going to be a lot easier to do in class because of having to use a colorimeter or spectrophotometer. You want a very kind of more sterile, not the sterile, but like a more controlled environment than being outside. ISEs, best to use them on site. What's great is you can get them calibrated and set up beforehand, and then just have them ready to go out when you go into the field and do an instant test when you're out there. The thing to keep in mind with ISEs is that they do have a module on them that does need to be replaced every 1 to 2 years. And that module has a shelf life. So what I recommend people doing is checking on their module. You can actually screw it off. I'll show you here. With our visualizer. So on both the LabQuest version and the Go Direct version of the ISEs, you have a module on the tip here that actually unscrews off. And then you can look at a date that's printed on the side here. This one, for example, says November of 17. So that one is very expired and needs replacing. That date can be hard to read, but can be found on the side of that module when you replace it there. And it's something that I recommend if you do want ISEs to make sure you work in your budget a replacement for the module every so often, and only to get those modules right before you're going to be doing these types of experiments. And like a lot of the other sensors, because it has this BNC connector, it is not waterproof. Same thing with the colorimeter, same thing with the spectrophotometer, not waterproof. Do not dip them in a lake or pond. Okay, we're in the home stretch here. So that's everything about the sensors that Vernier has that I recommend. There are some different helpful accessories that we have that could be useful also with doing water quality collection. One thing that I really like is for the Go Direct sensors, we have a sensor clamp. And I will point things out on the bench here in a second. This sensor clamp here is designed specifically for the Go Direct sensors, because when we came out with the Go Direct, I was like, that's awesome. These are great. They're going to be so much easier to use in the field. But I want to have a cord or something attached to it so I don't drop it in a lake and lose my sensor. So the engineers kindly developed me a sensor clamp that has a lanyard attached to it, so you can actually wrap it around your hand and ideally not lose your sensor into the raging river that you are measuring. We also have a water depth sampler that can be used to reach out into, if you don't want to use a kitty litter bucket like I did when I was teaching, these are great to use in ponds or off the side of small bridges, things like that, to get water samples. Somebody did mention the BOD bottles. So we do have water quality bottles. These are a plastic bottle that's been specifically treated to be non-reactive. And that's a key, making sure you have non-reactive bottles to collect samples in. And one thing that I like is if you're doing any macroinvertebrates, anything like that, it's cool to look at them at a hand lens. But there is a USB digital microscope that can connect to a computer or Chromebook that can have the students look really close at some of those organisms that I think are personally absolutely fascinating and terrifying at the same time. You could get a really good look at like a caddisfly, and it's basically a little cocoon that it's making. We also have a variety of different types of lab books available. So in a lot of our more bio-environmental, earth-centric books, we have water quality experiments kind of written up in those. We do have a water quality specific book. We are in the process currently of getting that updated for Go Direct sensors. It's not 100%. But if you already have the water quality book and you're wanting to use Go Direct with it, you can just shoot me an email and I could probably share with what I've done so far. I have not done much, but I do have some already done and available. So last minute kind of best practices for collection. The key thing to keep in mind is that there are certain measurements that really have to be done on site and within the body of water. Specifically, we're talking temperature and dissolved oxygen. It's not ideal to do those back in the classroom. But you can collect samples to take back to campus to read later. So for example, I was never able to go out directly during the school day to do water quality with my students, and we did not have a body of water nearby. So I would bring in samples for them to do testing on. And what I would use was airtight, non-reactive containers, ideally glass. And the idea is that you actually plunge the entire thing underwater and collect a sample without air bubbles being introduced into it. So the water should push all of the air out. And you want to make sure that it is absolutely filled to the top, that there is no air present in it whatsoever. That helps reduce the amount of oxygen being released or absorbed into the water. You also want to keep it chilled. So I would take a cooler with some ice packs in it and put the sample in there immediately, and then put it into the refrigerator when I either got back home or back to campus. And that's very important for making sure that you don't have decomposition starting and alteration of the chemicals that are present because of warming of that sample. I get a lot of questions of what if I don't have access to water? One easy option is if you have an aquarium, great. You can just use the aquarium as your sample place to get water samples. The other thing that I would do when I did NSTA workshops in different cities about water quality, I can't go out and get an easy water sample. So I would end up making my own water, and that would be a combination of using the tap water, plus some tea, plus some coffee, plus some bubbling to add some extra dissolved oxygen in there. I might add some spinach or grass or leaves to add some organic matter and basically make up my own soup. So that way I still had something that was more than just tap water for my students, or in this case, teachers, to be able to test. Chill at what temp range? Ideally, a refrigerator temp range is kind of where you want it to be at in order to basically you want to preserve the sample so decomposition is not taking place inside of it. Expanding beyond. So once you kind of do initial experiments with the students, you can really open up a lot of areas for if they're interested in doing some independent projects. One dream that I had was to do a long-term water quality project where my goal was to have students get water quality data at the same time every year. That way I could compare previous classes and they would have a large data set to be able to analyze. Sadly, that never happened. Aquarium monitoring is another great way. Looking at a comparison project. So for example, you have a water outflow coming from the street. What does the water quality look like above it or below it? How does a duck pond look compared to a pond without a large population of ducks? Before and after events, before a large rainstorm, after a large rainstorm, and then just doing up and downstream comparisons. There's a citizen science group that I'm working with that is monitoring a stream up above and below the different of a golf course to see what the effects that golf course is having on their stream. There were some questions and requests for NGSS alignment. We pulled out all the NGSS DCIs, SEPs, and CCCs that would correlate to water quality. I'm not going to go over the whole slide because we are very short on time and I want to get to questions. All right. So any testing for drinking water? We do not have any sensors that I recommend for drinking water testing. It's one of those, it's a rabbit hole that we would rather not get down because of the regulations and regulatory procedures around them. I know we get a lot of questions about doing lead testing, and we do not have, basically the chemicals in order to do any colorimetric lead testing are very, not something I would recommend to use in a classroom. Yes, extensive standard methods. It's a great resource to go to. Any other questions?
I think we got most of them answered as you
Awesome.
went.
So for those of you not aware, can we test for sulfur? We do not have a sensor for sulfur testing nor a chemical standard process for that. So one big thing, I don't know if you know, but Dylan is going to be doing a random person generator to select a winner of a Go Direct pH from this webinar. So keep tuned to your email to find out if you are going to be the one that wins that.
And I actually, I
Oh.
spun a random name selector already, and I can tell you who won. Pardon me. Our winner today is Charlotte M. So congratulations, Charlotte. You won a Go Direct pH probe. I'm going to email you here in just a second. So keep an eye on your inbox, Charlotte, and congratulations.
Yay, Charlotte. Congratulations on that. And thank you everybody for coming. I'm sorry I went a little long. Like I said, I could talk about water quality all night. And if you have any other questions that come up, do not hesitate to give us an email at biology@vernier.com or give us a call, or you're welcome to give us a chat as well. So we're here to help you. So make sure you let us know if we can help you. That's the most important part. Thank you, everybody.